Swayam Prabha. Digital India. Educated India.
Welcome to our MOOC course on high performance computing for scientists and engineers, and we are discussing architecture for parallel computing, which is part of the first module of the course, which is fundamentals of parallel computing. We are continuing the discussion from the last lecture. We discussed about architecture of a sequential computer. We discussed about interconnect networks, that means how are different computers connected in both shared memory and distributed memory arrangements, and we have also quickly looked into couple of terms like cache coherent protocols, fault sharing, and communication costs. And next we will look into some of the examples of parallel computing architectures, which are processor arrays, multiprocessors, and multicomputers. And then we will see some of the again the examples of practically working parallel computing large infrastructures, which are HPC clusters, and we will also look into GPUs. We will try to put some more detailed discussion on communication costs, and then we will discuss about Flynn's taxonomy. Processor arrays are the most initial days development in parallel computing, and one of the examples are the class they fall are vector computers. A vector computer is a CPU system designated to operate simultaneously on all elements of one dimensional array, compared to a ordinary processor which works on a single scalar only. So, if I write A is equal to B plus C, sequential computer will consider that A is a variable, B is another single valued variable, C is another single valued variable, and add B and C and get a value. If I use a vector computer, then A is a vector, A is an array or a vector, A has say 100 elements, similarly B and C have 100 elements. So, the same operation will be processed over all the 100 elements of B and C. There will be multiple computers which are doing same operation on different elements of a vector. So, instead of processing one by one of different elements on the vector, multiple elements of the vector will be worked on a go. And an example of vector computer is a processor array, which is a vector computer implemented as sequential computer, which is connected to set of identical synchronous processing elements capable of performing same operation on different data. That means it is the same operation which will be done, it is like a vector operation adding two vectors. So, same operation addition will be done all respective elements of these two vectors, and this will be done by different processors. Different processing elements which are synchronized are designated to do that. So, a vector computer again while saying so, I will show you also later, but we can tell that vector computers are not very much of use today, because they have some primitivity in their operation, they cannot work on complex algorithms, so we use something else now. Well, so but let us see what is in a vector computer. There is a CPU which has its own memory and IO devices. Now, this CPU is connected to a scalar bus to an interconnect network switch, and this interconnect network switch is further connects different processors which has their own small memory units, and they are again connected to a global result bus, and this result bus is connected to the CPU. That means scalar memory is one by one go from the CPU goes and resides in the memories of different vector processors present in the processor array, and these processor arrays have different CPUs, and they have each CPU is connected with their own memory, small memory part, and These memories, sorry, this is the scalar memory bus is connected to the memories of different small processors, small memories, and each processor is also connected with the interconnection bus, and the instruction goes from the CPU directly to each of these processors. They take the small amount of memory associated with that, work on them, and the result goes to a global bus which returns to the CPU. So, if we try to see, this architecture is taken from Quinn's parallel programming book. If we try to see in more detail, let us go to the next slide, that there are multiple processing elements, each has their own small memory, and if we have a large vector, parts of the vector or elements of the vector are residing on this memory, and this is the same instruction which comes from the CPU is replicated to all the processor. This processor takes the memory associated with that, processes the information, returns it to the global result to the CPU. Each processor has its own RAM M, but connected with a main CPU. Moreover, they share the same address space which is in the CPU memory. So, all these small memories are some way mirroring some part of the memory in the main address space. The vector processor's main CPU launches same set of operations through different vector processing parallel units to the processor arrays to different elements of the vector. It is the same set of operation which must go to all the processors. This is inefficient in running conditional statement for different processors. If different processors need to do something different, we use some if-else statement to make that. This is inefficient because these processors do not have well developed control unit also. They are supposed to work on the instruction which is given by the main CPU to them. So, if there are some complexity in between them, if there are some logical if-else type of logical reasoning statement in between them, it is an inefficient system, it cannot work properly there. This architecture is typically not in use today. However, some of the modern coprocessors like Intel's Xeon Phi or GPU architectures are inspired from this, that there are also many processing units which takes job from the instruction from a main CPU, and they do essentially similar works on different parts of the data. So, I said that these are typically not in use today. So, what is in use today? For that we need to look into multiprocessors. Multiprocessor is a multiple CPU computer connected with a shared memory. So, there is a bus or an interconnect network switch which is connected to a shared memory, and this memory can physically come in pieces, but virtually or in practice this is a same set of contiguous memory which is visible to all the processors. They have their own caches. Multiprocessors have different caches, but their memories map to the same address space. Even if some memory from this cache, some memory goes to cache of processor 1 and the same part of the memory goes to cache of processor 2, they must be mapped to the same address space. However, they may have some data, however it is also possible to give some data very specific to each of the processor, and this is called private data. We will look into private data when we will see threaded parallelization and especially OpenMP program, but the main data is shared. So, though the main, you can think of a joint account, though the main amount of money is visible to everybody, but everybody can have some amount of cash on their own money back. So, there is also some flexibility to maintain some private data which is not visible to all the processors. Processor 1 private data is separate from processor 2, but the main data is in this memory and visible uniformly to all the processors, and this is again called an centralized multiprocessor or uniform memory access multiprocessor or UMA. We have seen it earlier. cache. Now if one part of this data which is residing in its cache is updated, it must be reflected in the main memory, because this data might also be shared by the second processor, and if it is not reflected to the second processor's cache, then there will be a conflict. So say the variable A is called by first processor as well as, because they are looking into the same address space, processor 2 is also looking into variable A, and if processor 1 updates variable A from variable processor's 1 cache, it should come to the main memory and must also be reflected to processor 2's cache, otherwise there will be a cache inconsistency. So cache coherency is required so that shared memory updates are same in each cache, and this is done through write invalidate protocol. That means if processor 1 is writing something, changing some value in array A, then processor 2, 3, 4 cannot do that. There, if they try to write same on the same array, that write will be invalidated. So some data which is updated by one processor cannot be differently updated by other processors. And also sometimes processor synchronization is required for that, which is that at most if one processor is doing some activity and many processors are designed to do the similar activity, but it is mutually excluded that at most one processor is engaged on that activity. So if there is one variable all the processors are trying to update, the others will not be allowed to do that. At most one processor will be allowed to do that. There will be some sequentiality across the processors, and this is called a synchronization. And barrier synchronization, that no processor will move beyond a certain point unless all the processors have done that. So even if one processor has finished one work but other processors are also asked to do that work, there is a barrier synchronization put there. This processor which has finished the work cannot take the next instruction set till other processors have finished up to that particular state. These synchronizations are often given in multiprocessors. This is known as an uniform memory access or UMA, centralized multiprocessor is also known as UMA or uniform multiprocessor. There are also many very commonly referred to as symmetric multiprocessors or SMPs. They are also known as symmetric multiprocessor or SMP. Uniform memory access, because this is one piece of memory which is visible, one single address space, one piece of memory connected with the bus, which is visible by all the processors. This memory is uniformly visible by all the processors. The other variation of shared address space system is distributed multiprocessor or shared or NUMA, non-uniform memory access. Multiprocessors in a single bus has limited scalability, the previous arrangement shown, because it is a single bus in which you are putting many processors. You might not be able to put many processors on that bus due to space issue, due to electricity issue, due to heat generation issue. So one idea is that use distributed multiprocessors, where you can increase number of processors to a large extent. In distributed multiprocessor, each processor is attached directly to one piece of memory, and all the processors are connected via interconnection switch with each other. Like many processors, each processor has its own cache and own memory with own input output also, and all the processors are connected through an interconnection switch. However, we are talking about a shared address space system. Therefore, all these memories must map to a common global address space. So all these memories must be mapped to a global address space. So even if that means there is a global address space whose some part is residing here, 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 etc. And if there is some requirement to communicate, some requirement to access this data by this processor, this should go a request to the interconnection switch and look into the data. However, though they are physically different memories connected to different processors, but they point to the same address space. Each processor can access memory attached to it via non-uniform memory access protocol. That means the memory is not uniformly accessible by each processor. Each processor can directly access its own memory also, but this memory is mapped to the common global address space. Cache coherence supports are usually not available because each has its own cache also. Rather, there are some of the architecture which gives non-uniform memory access cache coherent protocol, but they are very inefficient system. There are large overheads. So rather directory based protocol which distinguishes between the uncached, shared and the exclusive memory. So for some part of the memory is known exclusive to processor 1, some part of the memory is known from processor 1 to shared with other processor. These directory based protocols are given while storing the data in the memory for this type of systems. This is NUMA or non-uniform memory access system. And the next variant is distributed memory, distributed processor. So if the memory given to NUMA systems, they are pointing to a common global address space. If they do not, that means that means they are different to different memories given and different address spaces given to different processors. We call it a multi-computer or a cluster, and this is really a distributed memory system. If the distributed multiprocessors do not map to a same memory, they are called multi-computers. Sorry, this is not multiprocessors, they are called multi-computers. That means multiple computers connected together through a interconnect network switch. It has multiple CPUs, each one has its own local memory and local cache. Local memories do not map to a single global memory, however they are connected to a single common file system through IO switch and internet, and some data through an interconnect network they can share some data from one processor to other. This is a scalable system because you can really, there are different computers, they are just connected through a network switch. You can use even a simple gigabit network switch which you use for your internet system. You can make an intranet and connect many computers and say that there is a multi-computer system, and actually can perform distributed computing HPC computations using that system. So and you can increase the number of computers in that using higher end switches, and you can have 10,000 or more computers connected together. This is a very scalable system. You can increase number of computers as much as possible. And one of the idea is called asymmetric multi-computer. That means there is a user who can talk to the internet, and through internet he can access the front-end computer, and the front-end computer is connected with interconnection network which is connected with many other computers. So if any job is given, it is given to the front-end computer and it launches it to the slave computers attached to it. This is called an asymmetric multi-computer. User can only log on to the front-end computer and instruct it to run a parallel job at the back-end systems. The front-end computer only needs to talk to the internet and user, therefore it has a updated operating system with all the functionalities. The backends are only designed to run some of the parallel applications which is launched by the front-end computer to them. So they have a primitive operating system. They do not need to have even graphics support. They are only supposed to do some of the arithmetic logical operations as instructed by the front-end computer. So and each of these computers have their own memory, and they are connected through the interconnect network and front-end computer to a file system where each of the computers' data can be written down. But while operating, they are operating only on the local memory given to them, and they do not point to a single common address space. And this is an asymmetric multi-computer. The other one is a symmetric multi-computer where the internet is connected to the interconnection network and it can access any of the computers. And these computers can communicate with other computers and make a group among them and launch a job. So each node has functionalities and can shoot parallel job alongside this with them. So this is typically you see a very well developed cluster with a head node and slave nodes, compute nodes, and this is if you have your own lab computer and connected through an internet switch, interconnection network, which is basically an internet switch, and then use another computer to talk to the internet, and you can access any of these computers, log on to any of these computers and launch a job. So both these arrangements are quite well used. This is again taken from Quinn's book. The next one is which is a more modern and more developed cutting edge application, is an hybrid HPC cluster. So this is a distributed memory, distributed node system, but now inside each node, so it's a multi-computer, each node has its own memory unit, but inside each node there are multiple multiprocessors. So each node is itself a shared memory multiprocessor UMA type of thing. So multiple computers are connected via high-speed MIDI-net switches. MIDI-net switches are high-speed network communication switches. Each computer has multiple processors with shared memory connected through interconnectors or same bus. So if you see then this is a scalable system and can connect near million processors. If we see that there is user internet which can connect to the switch Ethernet to a front-end computer, and then through the network switch front-end computer can launch job into multiple computers in between them, and each computer is like today's multi-core computer. If you buy a computer today, it is at least dual core 2 processor, that means 4-core computer. Similarly, if you go to each of these computers, they have multiple cores, so each of the computer is a multiprocessor also, which is connected to a local memory to the computer, but this is a shared memory space for all the processors inside the computer, and they are connected, apart from the Ethernet, they are connected through MIDI-net, which is a much faster network connection in between them. And by this you can connect 10,000 computers like this, and each computer can have few hundred processors inside it as a multiprocessor system. So by this you can have a near million processor system, and any of the HPC cluster is basically a hybrid HPC cluster with multi computers, and each computer is a multiprocessor. Each computer may be connected with GPUs or coprocessor accelerators to give better speed. And now if you look to a leading supercomputer, you will see that this multiprocessor computer arrangement is there, and each computer is connected with something like a GPU or coprocessor. So these are the most developed HPC architectures. And now we also quickly look into GPUs. A GPU card or a graphics processing unit card. These cards were initially developed by NVIDIA for gaming purpose. In gaming, there are different operations done on different parts of the computer monitor, and small computing cores are attached with different locations of the monitor, and they are taking of the development or the progression of the game at different locations. So for that they developed something which has many cores. This is taken from NVIDIA's CUDA guide. Many cores connected with this is the GPU card, which is a large dynamic RAM, which is almost comparable with a CPU, and many computing cores or computing units or small processors, each is connected with a very small control unit and very small cache, compared to a CPU where there is a large control unit and large cache, and 4 or 8 arithmetic logical units are there. But here in GPU there are in reality thousands of computing cores, but with very small control unit and very small cache. So when it is something like a processor array inspired architecture. When a job is launched, it is similar job which is executed by all the cores together, but this is a very simple job which they can execute, because the control unit as well as the register is small. They cannot execute a complex and large job. It's a simple small instruction which can go to all the codes and that can be executed together. So again, this GPU cannot work as standalone. It has to be connected via bridge to a host CPU, and we can see that if we can use GPUs efficiently, we can get performance much superior to a CPU. We can get even 100 times better performance than a very high-end CPU using a GPU, because many computing cores are provided here. The disadvantage is that as the cache and the control unit is small, we have to be very careful about writing the program and looking into the memory access during execution of any instruction in the GPU. Well, so these are some of the important computer architectures that we use for parallel computing, and now we come to something called cost of communication. We understand that memory access, if we talk about a distributed memory system, each computer has its own local memory, and they need to access different parts of the, if they have to ensure some continuity across the memory, one local memory given to one processor may have to be accessed by another computer. It cannot access, it's a different computer's memory. How can you infringe the computer and access the memory? So so in case one computer needs to know something about a memory which is residing in other's computer, the other computer has to send the data and this computer has to receive it. So in a distributed memory system, there is a requirement of frequent message passing across the computers. Some message which is in form of information or data has to be passed from one computer to another, and the other has to receive it. And this is called therefore these distributed memory systems are also called message passing based distributed memory systems. So we see into the latency and overhead due to communication through the interconnector switches. The message that goes, it has its own latency because it will take certain amount of time. It has some overheads also. This will add to the total computing time. So the computer, like we have seen for the cache for the sequential computer architecture, memory, RAM, CPU and DRAM system, that RAM's latency is adding to the performance of degrading the performance of the CPU actually. Similarly, for when they are connected through a interconnection network switch and communicating across each other, the latency, the communication time is adding up to the computation time, and the computing time is increasing. There are three components of the communication time. The first one is called startup time. The startup time includes the time to prepare the message by adding header, trailer, error connection information at the sending node, and the time to execute the routing algorithm. So first the message has to be prepared, then the routing algorithm, how the message will follow which route and reach where, the time to establish an interface between the local node and the router, and the time to prepare the receiving node. The receiving node must be ready for the message. If all these times are added up, this is the time to handle a message at the sending and receiving nodes, that this message is ready. Now the receiving nodes know that this message will come through this, from this computer to here, and the in between router is also ready for that. For any data transfer, this startup time or TS is associated with that. For any data transfer, first the message should be ready and the startup time should be gone to prepare the message. The next one is per word transfer time, that the time required to movement of the whole data packet from the network. So if there is some data, that is some information, some electric pulses which will go through certain path, and this electric pulse will propagate through certain path and reach another location. So depending on the amount of data or the bandwidth, how much data we are sending, there is a time spent on sending the data. And if bandwidth is r word per second, then time to send one data packet is 1 by r. If r words are going in a second, one word will go in 1 by r second. that is per word data transfer, and the total time for the net data transfer, if we have a data size m, that will be m into TW or m by r. Per hop time, if there are multiple nodes in the network, from one node to another node, in each node there is a latency, so there is a hop time th. If there are L links, the per hop time will be LTH. So the total data transfer time in modern network per hop time is usually much smaller than startup and data movement time. The total data transfer time is given as, for a data of size m over L links, startup time plus m into the per word data transfer time mtw plus LTH. Each message of size m will take this time to be transmitted over L lengths. So startup time plus the per hop time into the number of links, as many links will be there, more will be per hop time, plus the message size into the bandwidth, into the per word data transfer time. Now, if we do frequent data transfer, if we take a data and make it into break it into multiple components and send it at different goals, every time there will be a startup time, so the overall time will increase. So if we pack entire data together or multiple data together as a single message and try to send it, the startup time will be reduced. Similarly, there can be some other steps to reduce communication time. One is communicate in bulk, send data in packets, less number of data transfer operations will incur less startup operations. Minimize the volume of the data. If you can avoid sending some of the data, or if the total data size is m, if you can reduce this to a smaller number, the per word data transfer time will reduce. Minimize the distance between data transfer. Try to ensure the data goes from the neighboring processors, so that less hop links are there, so that the per hop data transfer is reduced. So these are three very essential steps we should think while writing the parallel algorithm in terms of in distributed memory, that this way we can reduce the data transfer overhead. For shared memory machines, the data access, there is a data access overhead, not data transfer overhead, because data is actually not transferred except for some of the non-uniform memory access applications. Rather, data is there is a common data space where multiple processors are trying to access the data, and there are issues like cache coherency, false sharing, etc. The components of communication time is basically the data access overhead time, that one processor is waiting till other can update its cache. So this communication time can be broken down as overhead due to cache access, initiating access to cache line of every contiguous data, mapping of local data to global address for NUMA machines, that it is local data for each processor, but they map to a global address. This mapping can take some amount of time. Cache thrashing overhead, false sharing. We will discuss about false sharing in detail when we discuss about shared memory systems. Contention between the processors, same data many processors are trying to write, so there will be some sequentiality in between them. Everybody cannot write at the same place, same location. This contention will be there. Invalidate protocol for cache coherency. If one is writing, the others will not be able to write, the others write will be invalidated, so they have to wait to get their turn. It can be observed that the communication time for shared memory machine, which is basically data access overhead, is also given as a constant plus a time multiplied by the data size. So in distributed memory, it was startup time is constant plus m into TW, data size into the time based on the bandwidth. Similarly, in shared memory also, the communication time is a constant plus time multiplied with the data size. So this is extremely important to understand that there is a substantial amount of time required for communication of data in a parallel computing system. Especially for distributed memory system, this time can be very significantly large and can sometimes reduce the performance of the parallel program. So we should be quite well aware of this time and should follow the right steps to reduce the data communication overheads. So we'll finish this part session now, and we'll continue with the discussion on different classifications of parallel computing architecture, which is Flint's taxonomy, in the next lecture.